Hello again. Time to talk about physics. This video lecture covers Chapter 7, Section 5, work done by a general variable force. So we're back to talking about variable forces. Remember our first example of a variable force, our most important example, in fact, of a variable force, is the spring force and Hooke's law. But now we want to talk about how you calculate the work done by any variable force, no matter what. Okay? All right. So how do we go about doing that? Calculating the work done by a variable force. Well, we're going to limit ourselves to a particle moving along one axis. Normally it'll be x, but it could be y or even z, but just one axis at a time. And it's acted upon by a variable force F. And so we have a picture down here below. And you can see we've got a horizontal x-axis, and then there's that applied force F right there that you can see is up and to the right, acting on our particle. And I've also sketched just the x component of that force. There you can see it labeled F sub x. That's just the x component of that applied force F. By the way, there are clearly other forces acting on this particle. There's F grav, there's F normal, there may even be frictional force. But this is the only one I'm looking at right now, okay? So somebody, maybe it's you, are pulling the block to the right with that applied force F, but you're not doing it with a constant pull. It's a variable pull, okay? And you are dragging this block from a location x1, initial, to a final location x2. Question: how much work does your applied force do? Now, we also have a graph. Let's look at this graph. On this graph, we're plotting the x component of your applied force versus the x coordinate. Note, when you calculate work, that it's only the component of the force in the direction of the displacement that can do any work. And so, that's why it's only the F sub x I care about. If what I want is the work done by this variable force, I only need the component of that force in the direction of the particle's displacement, and the particle's displacement is along x. So I only need to know the x component of this force. And this graph is one way to convey the x component of the force. And let's look at this graph. Let me highlight it here. It's that green curve right there. The point being that that F sub x is variable. It's changing. Yes? If it were constant, the plot of F sub x versus x would look like that. Horizontal line, constant value. But this graph that we actually have shows me that the force is changing because it's a curve, not a horizontal line for the F sub x. Now the way we calculate the work done involves this mathematical process called an integral. And that's this formula down here. And I introduced the idea for this when I talked about the work done by the spring force. But it's still the same idea. I have a particle moving along an x-axis from an initial point x1 to a final point x2. To calculate the amount of work done by the force, I integrate in this case, the x component of the force times a little tiny displacement along the x-axis, dx. So what this part here inside the integral symbol is doing is saying, imagine breaking up the x-axis between x1 and x2 into an infinite number of infinitesimally narrow rectangles, each of width dx, and height f sub x. And you multiply width by height, you're taking the area of one of these little rectangles. And remember, an integral is just a fancy sum, so the integral says sum up, add up all the little areas of all the little rectangles between x1 and x2. The net effect will be to find the area under the plot of f sub x versus x, and that's why that's shaded in there, all right, and labeled W. The work is equal to the area under the plot. So if we have a geometrical way to figure out what that area is, That's equivalent to doing the integral of f sub x times dx. Note the area under the graph, because this formula applies in any situation, is easy over here on the right when the force is constant. So you start at x1, you end at x2. The area under the curve, in this case, is just the area of this rectangle. So if you have enough information to get the height times the width, you've got the work done in that case. Okay, so bottom line, if you have a variable force, you have to do an integral. And if the particle is moving along the x-axis, then you take the x component of the force times dx, and you integrate from x1 to x2. Let me show you one more thing before I go on to the next slide. What if I have the special case shown on my graph on the right, where f sub x is a constant force? We actually already studied how to calculate work in that case, but let's apply this approach here with this quantity called an integral to the case of a constant force. Okay, so here on the right, this graph shows a situation where I have a constant f sub x, and the particle is moving from x1 to x2. The work is that shaded area where this height right here is whatever the number f sub x is, right there. What do we get for the integral? I'm going to tell you one of the many tricks your calculus professor is going to teach you about performing integrals. But one of them, it's probably one of the most important ones, is if the function you're integrating, we're integrating f sub x as a function of x. That's the function we're integrating. If it's constant, like my graph on the right shows, then you can bring that function out front of the integral. If it's a constant function, you can bring it out front. So I could bring the f sub x out front. And then I'm just have the integral of all the little dx's from x1 to x2. Add up all the little widths of all the little rectangles from x1 to x2. Well, that's just going to be, when all that's done, the difference between x2 and x1. How far is it from x2 to x1? You could, if you want, write that as f sub x times delta x, the change in x from x1 to x2. Note that this is exactly what we would have got by applying f dot delta r, because the force is constant. Now remember, this approach I just showed you is only valid if the x force on the particle is constant. If it's not, you have to do this integral. All right, now let me show you a special case that you want to just know, bottom line. What the special case is, what if the x force we're talking about has this special form? It's merely a polynomial function of x. The x force goes like a constant a times x to the power n, where a and n are constants, and n can be any value except it can't be -1 for the situation I'm telling you now. So, if you want to calculate the work done by a force like that, a force of that form, a polynomial function of x, then here's the step you have to do. You have to do the integral of that f sub x. You have to integrate a times x to the n power dx from x1 to x2. Now the multiplicative factor of a is a constant, and you get to bring that out front of the integral. So what you really have is a out front, integral from x1 to x2 of x to the n power dx. And I'm just going to tell you what that integral is. Okay? You have that a there, and then when you integrate x to the n power dx, you get x to the n plus 1 power over n plus 1. And your calculus professor will show you why that result is correct. But I will just mention one thing now that might make that seem a little bit plausible. I remember it did for me when I first came across this. If I give you a polynomial function, like that force function right there, and I ask you to take the derivative of it, notice the notation, I'll write it over here to the side. the derivative of the x force with respect to the x coordinate, then I'm asking you to take the derivative of a times x to the n. That you should be able to do. Polynomial function, right? You have a, multiplicative constant gets carried along. You bring down the exponent and put it out front, n. Then you multiply that by x and you decrease the exponent by 1, right? N times x to the n minus 1 times a. That's if you take the derivative of the polynomial function. As you will learn from the fundamental theorem of calculus, integration is the inverse operation to differentiation. So when I integrate a polynomial function of x, all right, instead of decreasing the exponent by 1, like I did here, we increase it by 1. See what happened over here in the integral? It became x to the n plus 1. And instead of multiplying by the exponent, like I did in the derivative, n, I divide, turns out, by the exponent plus 1. And the reason that's the right answer for the integral is because it has to be the case, fundamental theorem of calculus, that if you take the derivative of that answer for the integral, you get the same function f that you started with. You can check that if you take the derivative of a times x to the n plus 1 all over n plus 1, you get a times x to the n. Now you do have to put in what are called the limits to the integral, the x1 and the x2. And that's what I've drawn over here with this vertical line and an x1 below and an x2 above. That's called putting in the limits or substituting the limits. And what that means is substitute in x2 for the x, and then minus, and then substitute in x1. So that gets me this result right here. I have a over n plus 1, parentheses. First substitute in the upper limit for x. That'd be the x2 value. So you have x2 to the n plus 1 power. Then minus, and then substitute in the lower limit. So minus x1 to the n plus 1. So we do need to know and just be able to use this result for the work done by a force that's a polynomial function of x. I want to do a little mini example where we apply this new rule for a very famous polynomial function of x, the most important one, in fact, the spring force equation. In that case, remember f sub x, Hooke's law, is negative kx. This is known as Hooke's law. That's a polynomial function. Note then, compare that with my generic polynomial at the top of the slide, a x to the n. What is the a equivalent to in our Hooke's law? Well, what is the coefficient that's multiplying to x? In this case, negative k. Right? So in Hooke's law, comparing Hooke's law to the polynomial form of the force, a corresponds to negative k. What does the n correspond to in the polynomial form of the force compared to Hooke's law? Well, the x in Hooke's law is raised to the 1 power, right? That's what that means. So the n is 1. So now let's get the work done by the spring force by applying my generic formula for the work there in the boxed equation in the middle. Okay? A over n plus 1 times x2 to the n plus 1 minus x1 to the n plus 1. So a, negative k, over n plus 1. Well, n is 1. 1 plus 1 is 2. So negative k over 2, parentheses. x2 to the n plus 1, but n is 1, and 1 plus 1 is 2. So x2 squared, x final squared, minus x1 squared, and x initial squared. If I don't like that negative sign out front, I can distribute it through the parentheses, and I get my final answer for the work done by the spring force is little k over 2, little k, remember, is called the spring constant, times x1 squared minus x2 squared. Little k over 2 times x initial squared minus x final squared. And that's the formula I talked about in great detail in the previous video lecture. The formula we will use for the work done by a spring force. But now I've got in the middle of this slide the formula I can use for the work done for any generic polynomial function of x. The only thing I can't use it for is if the n exponent there is equal to -1. You see where the problem would be? Look at that denominator. There's an n plus 1. So if you try to substitute -1 for the n, you end up with a 0 in the denominator. That's a hint that this formula that I've got here isn't going to work for n equals -1. You have to do that integral as a special case, and again, your math professor will do that. We won't need that for a while. Okay, so that's work done by a general variable force. So one of the things I'm going to do in class on Friday is a Wiley plus type problem where we have to calculate work done by a variable force. And remember, there's the integral expression for work, but remember, an integral is area under a curve, and that's also the handy thing to remember, as you'll see when I do that example problem. All right, but I want to go on now to one more topic in this video lecture. And now I'm moving on to one more section in Chapter 7. Chapter 7, Section 6, where we introduce in physics the concept of power. Another one of those words that people use a lot in daily life, but has very specific definition in physics. Bottom line is this. This chapter has been concerned a lot about forces that do work. But one of the things we haven't talked about is how rapidly work is done. You might have a large amount of work done, but maybe there might be a situation where you're interested in not only how much work is done, but how quickly is it done. After all, a glacier moving at a glacial pace, say through a valley, does huge amounts of work on boulders as it pushes them down the valley, right? So a glacier can do a huge amount of work as it pushes big boulders across a valley, but it does it over a very long time. Whereas an electrical motor, say, that lifts an elevator cab, will do a pretty large amount of work over a much shorter amount of time. So there may be situations where we're interested in not only how much work is done by a force, but how rapidly is the work done by the force. So to set ourselves up for this, let me talk about the following scenario. Basically, it's like the one I just talked about. I've got a particle moving along a horizontal surface. It's moving from some initial location 1, x1 on an x-axis, to a final location 2, x2 on the x-axis, and it takes an amount of time, delta t, to do it. And there are forces acting on it. In this case, I've drawn the particle in the free body diagram. There's F grav down, F normal up, and I've got an applied force. Maybe that's me pulling on it. Apparently there's no friction in the diagram, isn't there? That's okay. And I also draw just the x component of my applied force, right there, F sub x. And I also show the displacement vector from point 1 to point 2, delta r. So that's all the stuff that's going on. Okay? I've got a force F, it's doing work on a particle that moves from x1 to x2, and it does that in a time interval delta t. All right, let's first talk about the work done by the applied force. I'm going to highlight the work done by the applied force F. Well, since I don't know whether the force is constant or variable, the safest approach is to express the work as an integral. I integrate the x component of the force times dx from x1 to x2. If the x force is constant, if it is, this becomes F sub x times delta x. F sub x times x2 minus x1. But that's only if F sub x is constant. All right, so one way or another, we have to correctly calculate the work done by this applied force, WF. Here comes the definition of average power due to the applied force. Okay, symbol, capital P, subscript AVG, it's called average power, and I like to add a subscript telling you what force is responsible for this power. in this case the applied force F. So the definition, note the 3 lines, of average power due to a force F is the work done by the applied force divided by the amount of time it took to do that work. The amount of time it took the block to move from 1 to 2. WF over delta T. Okay? The work done divided by the amount of time it took to do that work. That's what we mean by average power due to a force. What's the SI unit for this new quantity we've just defined called average power? Well, it must be the unit of work. Technically, that's Newton times meter. But remember, Newton times meter unit is equivalent to the unit called a joule, the unit of energy. So it's often expressed as 1 joule per second. And the unit joule per second is given its own unit name. It's called the watt. And you've probably heard that name. Think of light bulbs. Okay? The watt is the SI unit of average power. Okay? And it's basically how much work in joules is done per second. Now, there's a little more to power than that. In addition to instantaneous power, in addition to average power, we can talk about instantaneous power. We can define it. Instantaneous power due to the applied force. That'll just be labeled P sub F. Defined to be, well, it's basically the average power in the limit as delta T vanishes. And what you end up with is a derivative. It's the derivative of the work with respect to time, or the rate at which work is done. Okay? That's what instantaneous power is, the rate at which work is done. What is the rate that work is being done at a given moment? Note, in order to do that derivative, dWf dt, you need to know the time dependence of the work done by the force. You need to know how Wf is a function of t. How does it depend on time? Then you take the derivative of it. If you work out, no pun intended, that the work done by the force goes like some constant times t cubed, then the instantaneous power associated with that work is the derivative of that work with respect to t. And there's the work function, at cubed, and that's a polynomial, and the derivative of that would be 3 times a times t squared. That's all you got to do, if you know how the work depends on time. Now let me tell you an alternative expression for instantaneous power. It's equivalent to the derivative I just showed you. But sometimes, often, it's the more handy way to calculate instantaneous power associated with a force. It's right here. It's a scalar product. Take the force vector we're talking about and take the scalar product, the dot product of it, with the particle's instantaneous velocity. F dot v. Okay, but these instantaneous power expressions still have the SI unit of watt, joule per second. Let me end the lecture with a little bit of practice with instantaneous power, okay? Because I think that would be helpful. And then we'll talk about that in class as well. All right, let's take one-dimensional motion in which a child on a sled is pulled across a frictionless horizontal surface by a rope under constant tension that makes an angle theta above the horizontal. Let's draw a sketch. That's the horizontal ground. That's an x-axis. The child starts, let's say, there at time 0, presumably with a velocity of 0, and is being pulled along. There's the child on the sled by the rope under tension. So there'll be a tension force up and to the right that makes an angle theta with the horizontal, and that little arrow right there is the x component of the tension. Note that that x component would be magnitude t times cosine of that angle theta. And the tension force is constant. And let's say that this is where the block, or the child on the sled is at a later instant in time. But I'm just going to denote t. T could be anything. It could be 1 second, 3 seconds. It's just arbitrary. Okay? But the child is moving at this time, so the child would have a velocity to the right. And up to this point, the child has a displacement too. Let me draw it right here. Delta r. Okay, so those are all the important vectors in my drawing. Child on a horizontal frictionless surface, child on a sled, pulled by a constant tension force that makes an angle theta with the horizontal. The first question is, what is the time dependence of the work done by the tension? Work done by tension force as a function of time. How does it depend on what the time is? And turns out it's a multiple choice, and they give us 4 options. The work done by the tension force goes like the time squared. It's proportional to t squared. The work done by the tension force is time independent, i.e. it's constant. After all, the tension force is constant, so why isn't the work done by it constant? The work done by the tension force goes like the square root of time, or the work done by the tension force goes like time to the 1 power. It's one of those 4. Which is it? Let's figure it out. Since the force is constant, the tension, to calculate the work, don't have to do any pesky integrals. To calculate work done by a constant force, your starting point should be force dot displacement. And don't just say times, say dot. Because dot means dot product, scalar product, and will signal to your brain, hopefully, that you have to do all the formalities of the dot product correctly. The displacement delta r, as you can see, is totally along the x-axis. So I'm going to change that notation to delta x. And therefore, it's only the x component of the tension that survives the dot product. So it simplifies my work formula for the tension to that. The x component of the tension times the x displacement. All right, now, the x component of the tension, by golly, that is indeed constant. But what about the delta x? What's the displacement of the particle along the x-axis? Depends on the t. But you know what? All the forces on this child, this particle, are constant. Yes, all of them. There's the tension force from the rope, but I'm told it's constant. There's F grab, down, constant. F normal, up, constant. No friction. All the forces are constant. So the net force is constant. So Newton tells me the acceleration is constant. Aha! The constant acceleration equations are now at my disposal. But I know the formula for delta x. It's constant acceleration equation number 2. Delta x equals v initial x t plus 1/2 a sub x t squared. But v initial is 0, so it simplifies to 1/2 a sub x t squared, where the a sub x is constant. I know that from Newton's second law. So when all the dust has settled, the work done by the tension force is, let's put all the constants together, multiplicative constants, and then I'm left with t squared. Right? All the stuff in the parentheses are constants. So the functional form of this result is just a constant times the time variable squared. It's a polynomial function of time, and it goes like time squared. So the answer to part 1 is A. The work done by the tension force grows like t squared, time squared. So even though the tension force is constant, the work it does grows quadratically with time. Now here comes question 2. What is the time dependence of the power associated with the tension? P sub capital T. And if they don't say otherwise, if they just say power, they mean instantaneous power. So I want to know how instantaneous power of the tension force depends on time. Well, we just introduced how you calculate instantaneous power, and one of those ways, in this case it's the power associated with the tension, is I take the derivative of the work done by the tension force with respect to time. And since I found in part 1 the formula for the work done by the tension as a function of time, it's just a fancy constant times little t squared. It's not hard to do that derivative. A constant times little t squared is 2 times the constant times little t to the 1 power. So this is 2 times 1/2 capital T sub x, a sub x, little t. And it's the 2 and the 1/2 cancel. If you want to simplify that, you're welcome to do so. And you just get capital T sub x, a sub x, times little t, where this stuff right here is a constant. And so I see that the tension, the power associated with the tension grows linearly with the time. Okay? Grows linearly, like t to the 1. So the correct answer for question 2 is D. The power associated with the tension force grows linearly with time. Now let me show you one more way to calculate that answer to question 2. What is the formula for the instantaneous power associated with the tension force? And that is to use the second way I showed you to calculate instantaneous power for a force. It is to take the dot product of the force with the velocity. In this case, the force is the tension force. Now look at my picture up here. See the tension force, the green arrow? See the velocity vector, the red arrow? I need to take their dot product. Notice the only component of the tension along the velocity is x. So when you do that dot product of t dot v, that's an interesting dot product, right? But that's what the formula is I take the x component of the tension times the x component of the velocity, which is the only component of the velocity. All right, so you say, okay, so now remember, the acceleration is constant. So again, the constant acceleration equations are available. How about constant acceleration equation number 1? V sub x equals v initial x plus a sub x times little t. But v initial x equals 0. So what I'm left with here is a sub x times t. So the instantaneous power associated with the tension, just do a little grouping, capital T sub x times a sub x times little t. And I get the same expression I had over there. Okay, so what we're going to do in class on Friday is, and probably over into next Monday, we're going to do a Wiley Plus problem that involves calculating work done by a variable force. And then we're going to do a Wiley Plus problem that involves power. Okay? All right, but that will be on Friday. For now, that's all for this video.